Hi, I'm John Janowick. I'm the Executive Director of the Electrical and Computer Engineering Department Heads Association, and welcome to the Industry Spotlight Sessions. We're pleased today to have MathWorks presenting their topic, 10 Ways to Accelerate Education with MATLAB and Simulink. Today's presentation is being brought to you by Todd Atkins, Education and Technical Marketing Director of MathWorks. Todd?
Thank you, John. Thank you for all of those great introductions. So as John said, my name is Todd Atkins. I'm an engineer with MathWorks. I would describe myself as a lapsed EE because I got the degree but never actually worked in hardware anywhere along the lines. I went straight into software. So my responsibility at MathWorks is to manage a team of engineers who are responsible for supporting educators and their goals in the classroom with MATLAB and Simulink. So my intent for today is to cover something on the order of 10 features of MATLAB and Simulink that I think are relevant for you in your teaching goals. When I created this presentation, I thought I had 10 minutes to present. So I was very excited when I had 15 minutes, which means I can breathe in between the features. So this is good. So as most engineering instruction starts off with pencil and paper in the classroom. At some point, you move beyond what you can conveniently cover with pencil and paper, doing that symbolic computation. Symbolic Math Toolbox allows you to cover larger problems, more complex scenarios using that same symbolic notation, and allows you to integrate that functionality with the MATLAB environment so you can bridge that gap from pencil and paper to the computation that you're doing in the later classes. Last fall, with the release of R 2012B, we replaced the menus on MATLAB and added in a tool strip. The tool strip makes it easier for you to find features and for your students to find the features that they need. One of the nice features that we added with this tool strip is now there's a plot gallery. So instead of searching around for, okay, what's the plot command to generate that visualization that I want, you can search for the particular plot that serves your needs. About 9 years ago, we added a rapid prototyping-like functionality to the MATLAB editor. So within the MATLAB editor, you can right-click on any numeric value and pull up this little palette. In this palette, you can use the increment, decrement buttons or the scale buttons to shift the numeric value, and as you can see, it reruns the code, regenerates your image, so that you can actually interact with your code. This is a convenient way to do quick parameter sweeps or show the effect of changes in parameter choice live to your students. Once you've generated your code, we see a lot of faculty who have their MATLAB code and a Word document. And they write up their description in the Word document, run their MATLAB code, paste the MATLAB code in, paste the image in, and use that to generate their handouts. Again, about 9 years ago, we added publish functionality to the MATLAB editor. So within the editor, you can use the buttons on the tool strip to add markup to your comments, bold, italic. You can insert lists, numbered and bolded lists, LaTeX expressions, right in the MATLAB editor, and then you can click on the publish button. When you click on the publish button, it runs your code and generates a handout for you from your original code. So this will render all of your comments with that markup I talked about, including the LaTeX expressions. It will pre-print your MATLAB code and insert any visualizations that you have, any plots and graphics that you have, so you now have a single file that you can hand out to your students, or have your students use in the reverse direction to hand in assignments to you. So you can see their calculations, rerun their code, see their output. Using this functionality, you can generate Word, PowerPoint, HTML, PDF, LaTeX, and XML documents. So walking around this conference over the weekend, I see almost everybody has an iPhone or an Android device. Part of what makes those so useful, besides the performance that they have, is this vast universe of applications or apps for them. Apps are generally a relatively small piece of software that serves a sort of niche goal for you, accomplishes some particular task for you on your device. Again, last fall, we released MATLAB app functionality. So these are MATLAB applications with all the power of MATLAB that generally have some interactive or visualization component that you can use to illustrate phenomena to your students. This particular one is an eye scope for analyzing eye diagrams. Part of what makes apps so convenient is the ability to discover them. You scan through the home screens on your phone or go to your program list. You see icons there for the apps that are relevant to you. In this case, again, because of that tool strip functionality, you have an app gallery for all the apps you have installed with MATLAB. The other thing that makes apps really powerful in this phone ecosystem is the ability to find more of them. You can go to the iTunes App Store. You can go to the Google Play Store. Using the Get More Apps button on the tool strip, you can go to MATLAB Central and download any one of a number of free apps that have been contributed by the user community. Additionally, these apps are a single file. So if you fetch them from within MATLAB, they'll install automatically. If you distribute them to other users, it's a single file. So rather than handing out code to your students as a zip file that they need to extract and configure their path to run, it's now a single file. They can click on it, install it, and run it right away. Additionally, one of the things that is available in MATLAB, which is a bigger challenge on the iPhone, is you can write your own apps. You can take your MATLAB functions, your MATLAB GUIs, click on the Package App button, and pull up this UI that allows you to specify which files to include in the app, enter a name and description, maybe an icon, and generate one of these app files. I have to admit, after the presentation yesterday, talking about the Apple design, Google design, the way you design your applications, I was a little hesitant about putting up this screenshot. So shifting gears dramatically for you, how many people use Simulink? Yeah. That's more than I expected. That's good. So for those of you who didn't raise your hands, Simulink is a graphical design environment for modeling and simulating dynamic systems. Within Simulink, you have blocks for various math and analysis functions. You can additionally insert MATLAB blocks and put your own MATLAB code in there. And with the most recent release of Simulink, we offered a number of functions that make it much easier for you to build and for your students to understand Simulink models. Features such as being able to disable or comment out individual components of the model, much like you would in your code. The ability to step forwards and backwards in time in your Simulink model. And the ability to add conditional breakpoints. So you can look for the occurrence of a particular phenomena in the model, and then your students can investigate the causes of that phenomenon by stepping through the model and interrogating the model at different times. In 2009, the IEEE Control Society did a survey of industry and academia, and 83% of the industry respondents said that state machines were either essential, important, or useful for their industry. Unfortunately, only 33% of faculty said that state machines were a key part of the curriculum. I was lucky in that my professors were in that 33%, so state machines were fundamental in my understanding of computation in my introductory courses. But in doing all of those, they were still just dead tree assignments. We drew out state machines. There was no way to interrogate them, to validate them. They were looked at for correctness. With Stateflow, you can build state machines in a graphical environment as part of Simulink. And it wasn't all fuzzy and wavy on me on my computer, but you can build these state charts, draw your states, draw your transitions, and then run that as part of your Simulink simulation, and use those same breakpoints, the step forward and backward, to see what caused a particular transition at a particular time to really debug and understand your system. There was some conversation yesterday about the notion of a system. And several of the industry participants were talking about, well, from one perspective, the system is the combination of transistors. From another perspective, it's the engine and the wings and the control stick. There are various different views of what a system is. And we don't ever do engineering in isolation. We want to do engineering within the context of that particular system. Within the Simulink world, you can insert these systems in various different domains. So within Simulink, you have controls, signal processing, all of your algorithmic functionality. Additionally, you can add electrical components like resistors and capacitors, add mechanical components like linkages and joints, and add gear components as well as hydraulic components. So you have this array of different domains that you can incorporate to build up a larger system. And then you can expose your students to either working on different aspects of the system, working on the whole system. You can now have them build a control system instead of to a spec, to a particular mechanism. So there's been a lot of conversation as well about hands-on education. And there's the debate about whether you can do everything in simulation or whether you need actual hands-on components. Regardless of that debate, there are times where simulation is the only feasible option. There are a number of different simulation environments that are coupled with MATLAB and Simulink. One, in the bottom corner, is Simulink 3D animation, which allows you to do a full 3D visualization, live 3D visualization of your system running. You can build this with a VRML editor or use a 3D modeling package like SolidWorks to generate the 3D model that you then connect up to the MATLAB and Simulink environment. And now you have, instead of looking at a plot of where your robot has gone, you can watch the robot drive, see where it wobbles, which is a much richer experience. The simulator on the upper side is something called SimIM, written by some faculty at Georgia Tech. So SimIM is a robot simulator for a differential drive robot. It again starts to give some of that rich feedback that you get from a simulation environment. So you can see it animates what the sonar rangefinders detect. They turn red when they detect an object in their presence. And this simulator is used in some introductory controls classes, as well as in a control for mobile robotics class that's currently up on Coursera. That's one of the challenges with physical hands-on education that everyone is trying to solve, and there have been a lot of strides to that effect, but how to do that for 40,000 students. SimIM is in use by 40,000 students on Coursera today. Additionally, Cornell has created a simulator for the iRobot Create, which is a similar platform. And Drexel University has built a simulator for USRSim. USRSim is a full-fledged gaming environment where you have a full physics engine backing the simulation, and so you can drive your robot around and up and over things, etc. And it's a very powerful environment that actually arose from the task of trying to design search and rescue robots. But I'm inclined to agree that there are times where simulation is not sufficient. We have increasingly better tools to build better and faster physical platforms using things like Kinects, Lego, and 3D printing. We have, thanks to the semiconductor industry, increasingly powerful and inexpensive platforms for embedded control applications. And you can couple these together, but we still run into the problem of writing that C code to actually manifest the device. With Simulink and MATLAB, we've reduced that to a single menu item. So you can take your system that runs on any one of a number of platforms, including Arduino, BeagleBoard, Lego, Raspberry Pi, and with a single click, run that on the device in the embedded scenario. So I hope I've covered sort of a range of functionality that is useful, at least some of which is useful to you and your colleagues in the classroom. If you have any questions about any of this, come by and catch me at the booth or catch me walking around over the rest of the conference, and thank you very much for your time.